Welcome everybody in the lecture hall, welcome everybody on Zoom, welcome everybody from the future. Today we are going to finish what we started on document stores, which is kind of an equivalent of PostgreSQL, except that it's not for tables or for SQL, but it's for collections of trees. And we see that collections of trees are a generalization of tables for two reasons. First, because they allow for nestedness, while tables do not. And second, because they allow for heterogeneity, which tables do not. And heterogeneity means you don't have to have a schema. It can also be a big mess in your collection, and that's actually fine too. So the reason I say it's like PostgreSQL is that you need to import your data in it, just like you do when you use PostgreSQL. You cannot just dump your data on a data lake like on S3 or HDFS. That's a totally different paradigm. And so we saw that once your data is in there, you can actually start querying it with a query language that looks like this. So the most important thing to know about the query language, the most famous command is the find command, which is invoked on the collection. So here you put the name of the collection, db.thename of the collection.find. That's the JavaScript way of doing that. And the first parameter is the selection or the projection. Anybody remembers? Who thinks it's a selection? Who thinks it's a projection? Okay, we need time to wake up. It's 8 a.m. So let's do it gently and smoothly. Okay, so here, this is the selection because we look for all the objects that have theory relativity. So this one and this one. And here it's a projection because we say what fields, what keys we want to have. So first, last means we only pick first and last and we drop the rest. Just some remark. In the context of document stores, the name that we give to the JSON keys, we might not always say key. You might also hear field, property, colon, attribute, and so on and so on. So just don't be too worried about that. It's just that there are plenty of synonyms to say the same thing, right? So it just means key. And the equivalent query would be that first and last would go in the select, which is a projection, and then the where clause, which does the selection, has the predicate, right? So I showed you a few queries. I showed you how we handle heterogeneity, where the types might not be the same everywhere. We saw that in MongoDB, null is the same as no value at all. So absence of value or null is the same. And so if you put null in your query, it's looking for the documents that are missing the value or where it is null. And yeah, and we also saw what happens in the case of nestedness, right? Okay, so I also told you that the dollar is special. It's not treated like any other characters. And that's because there's a whole series of special commands, magic commands that start with a dollar. We already saw one that's $OR that allows you to have the OR logical operation, so $OR. And we also have the comparisons like $GT for greater than and so on, right? Here's another one that is $in. $in, it's actually a bit like OR. It basically says university has to be one of these in the array. So it can be ETH Zurich, it can be EPFL. And then when you go there, it's going to accept this document here, and this document is not accepted because it's not in the array, right? Who understands $in, what it does? Okay, it would be equivalent to having $OR and then university, ETH Zurich, university EPFL, right? I could also have done it with a $OR, but it's more compact. Okay, there's another one called $nin, not in, which is the opposite of that, right? It's basically excluding. So anything that is in here is excluded. So this is excluded, right? It's not returned. And this one is returned because it's not in there. And there is actually a whole list of operators like that. You can look them up easily in the documentation of MongoDB. It's not necessary to know them all by heart, but typically what people do is they look at the documentation, right? Something also to make sure you're not worried too much. There will be no programming assignment with MongoDB on exam day, right? So you won't have to actually write any queries with MongoDB, right? It's only PostgreSQL, PySpark, SparkSQL, and JSONic. These are the four. But MongoDB, you might have theoretical questions, or we show you a few queries and ask questions, but you will not have to actually write any queries, right? So the pressure on you is much less than with the other languages. Okay. Then find is not the only function out there that you can call. There is a series of others, like count, for example. You can just do it after the find. You might have heard, many of you probably know a bit of Java or C++, or they have seen already how you can call what's called a method when you have dot something. Who heard about methods, functions? Okay, some of you. The idea is that we take the output of find, and this dot count, it's like it's a pipeline. And then you count the number of documents that are returned by find, right? So in that case, that just says, for example, 10 or 1 million and so on. It just tells how many there are instead of showing you the results. Okay, here's another one. Something else you can do is sort. So you can ask to sort by founded -1, that means decreasing. -1 is decreasing, 1 is increasing. And here you would sort the results by decreasing year of foundation. Okay, that would be the equivalent in SQL of what is the SQL equivalent of this? Yes? Yes, almost. It's called order by, but that's exactly it. It's exactly the idea, right? So order by founded descending, exactly. So indeed, okay. And skip and limits, they also exist in SQL. Skip is actually called offset in SQL. So that's offset 30 in SQL and limit 10 also in SQL, right? But you see that in MongoDB, it's just because it uses JavaScript. So there's this chain of dot function. This is the reason why I do not consider this to be a query language. This is more like some programming interface that you can use in programming languages to call. It's similar to Spark transformations. Actually, when you call Spark transformations, it's a bit done that way. It's very important that you understand the difference between a query language like SQL that doesn't have all these dots and parentheses, that is just looks like English almost. And on the other hand, these programming interfaces, they're called APIs, that allow you to build your queries in a programming language, right? So it's important you have this intuition of query language versus programming interface. Okay. Here's another one you can also call distinct. On the entire collection, you don't need find here, and here it actually looks for all distinct values of last, right? That also exists in SQL. I think you can write something like select distinct lasts, and it will do more or less the same thing, right? So that also works. And finally, and I only have one slide for that, but you will quickly understand why I only have one slide for that. There is also something called pipelines in MongoDB. That's the function aggregates. And look what we have in here. It's just a series of things that we do. We have a match century 20, then we group by year and counts for every year, then we sort, then we limit. Doesn't that not ring a bell? What does that remind you of, this thing here, this pattern here? Do you recognize something that we've covered in the lecture before? Yes, maybe? Yes, exactly. It's exactly the same idea of MapReduce and also Spark, which is the most modern MapReduce. That's exactly it. That's exactly the reason why I only have one slide, because that's exactly the idea. Here, it's basically the first one match would be a Spark filter. The second one would be a group probably creating the pairs and then grouping by key. Then you would have a ordering, and then you limit and so on. And you can also do it in MapReduce. And in fact, I think in the early versions of MongoDB, it was more inspired by MapReduce. And then over time, it evolved to a more full-fledged API. All right. Who understands what's going on here? Who could write an equivalent SQL query? I think most of you could, right? And that's exactly why I'm not showing anything else than that. We've already seen that. It's Spark. We've already covered it. So if you were interested, you could read the documentation of MongoDB, but you would not see anything new in there. That would just be something you already know. Okay, so this is it, right? More like MapReduce, as you said, and Spark. All right, but of course, that's very scary to do things that way. And this is why we'll cover JSONic in the next lecture, which is a more user-friendly way of handling nested heterogeneous data similar to SQL. Okay, So the functions that I've shown you so far were all functions about querying data, but you can also update data just like you can in SQL. You can insert documents in the collection, you can update documents, you can also delete documents. So just very quickly, insert one would insert one document, update many would set the century to 20 whenever last is Einstein, but it might occur multiple times, and delete many would delete all the documents where century is 15. And there will also exist insert many, update one, delete one, everything exists, right? So the one thing you need to know here is it is possible to update the collection, delete, insert, update, and so on. That's something you cannot do in Spark or MapReduce, right? Spark or MapReduce, data lakes, you can just scan or read the whole thing, but you cannot modify the document because we don't have random access on the data lakes. So this is a huge, nice feature of MongoDB or PostgreSQL. These are because you import the data in there, and as a nice benefit, what you get back is the ability to modify it. Right? So insert, update, delete. Okay. Whenever you update things, the granularity is one document. What do I mean with that? You might have 100 people talking to MongoDB at the same time. If it's installed in a company's servers, you might have 100 employees, and there's a website, and there's millions of people visiting it. What I mean with granularity one document is that you never, ever have anybody touching the same document at the same time. If two people want to touch the same document, they will have to queue. It's first one person, then the other person, right? However, within the same collection, you might have several people looking at different documents at the same time. That's totally fine. So this is called granularity or atomicity. Okay, so that's the granularity. The equivalent in HBase, what would be the granularity in HBase? The equivalent of this? You remember in HBase? Anybody on Zoom? It's a row, right? In HBase, you cannot have two people touching the same row at the same time. The granularity of a row. Okay, but it shouldn't surprise you because a row in a table is just like a document in a collection, right? We saw that it's the same thing. Okay. It turns out that, as I told you, this is not a query language. This whole thing with the find and all these functions in JavaScript, it's only a programming interface. But there are plenty of languages out there, and we'll cover them in the next lecture. Some other document stores do have higher query languages, and I just to name a few, Uncle, XQuery, JSONic, GraphQL, we might have heard by Facebook, and so on and so on. Nickel is also one. So there are probably 30. I keep counting them. I think there's probably 30 languages. We don't have the luxury of SQL that has there's only SQL for tables. So here we'll need time to consolidate. All right, but this is for the next lecture, these higher level query languages. Okay, now a bit about the architecture of MongoDB, but here I'll go quickly because again, there's a lot of things you already know, and it's just to give you a general idea of how that works. First, what should not surprise you is that MongoDB replicates the data. It's also not new. We also saw HDFS replicates the data as well, and so on, right? So MongoDB replicates the data. It has several copies of every document. That's the first thing. Second, MongoDB has the idea of chunks or shards or splits or partitions that we've seen everywhere. We've seen them in HDFS, we've seen the region in the HBase and so on. It's the idea of cutting the data into plenty of different partitions. So that shouldn't surprise you because MongoDB also does that. It also cuts the data into different parts. That's called clustering, but it doesn't really matter how it's called, it's just the same. So in that case, for example, for a specific field or key in the documents, A to E is in the first shard, F to P is in the second shard, and Q to Z is in the third shard, right? And you can have many shards. It doesn't scale up as far as HDFS that could go to many thousands of shards. In MongoDB, typically in the typical setup, you might have 5 or 10. Maybe, I mean, it doesn't go as high, even though there was progress in the recent years. All right, but you see, we replicate the data and we shard the data. So this is not new. Now, in terms of architecture, it is a bit different. It is a bit different from what we saw in HDFS and S3. We still have this idea of having primary and secondary node or coordinator and workers or whatever you call them, except that we have this centralized architecture for every replica, meaning that we have several of them like this. There is a first shard, a second shard, a third shard, and we every time have a tree like that. This is new. This is something MongoDB does differently from HDFS, right? So in that case, you would need 9 computers in order to do that. That's the reason why the typical setup of MongoDB doesn't have thousands of machines like you would have in HDFS, but more 1 or 2 digit number of machines typically. All right. And the idea is that when you write something to MongoDB, it goes to the right replica, right? Depending on what you want to write, then it's going to put a copy here. And then, because I said it builds replicas, it's also going to have replicas on the other machines, takes a bit of time to propagate. And then at some point, you're happy because you have enough. In that case, for example, you might have requested that you need at least 3 copies to be happy. And if you're happy, then it stops, it returns, and that's fine. And then it might continue to replicate more in the background, but as a user, you're satisfied. You can change that. If 1 copy is enough, then that's fine. It will stop as soon as it has 1 copy, or you can be super cautious and ask that every server must have a copy. So in that case, you would request for 6 copies in order to be happy, right? For whom is that clear? For whom is that not clear? For whom is that clear? Okay, I see some notes. Very good. All right, so you do have a bit of control. But you see, it's more physical than PostgreSQL. In PostgreSQL, you don't have to worry about these things, right? So here you have a bit more view about what's happening. Okay, so now the second part of MongoDB that is extremely important because this is something we do not have in MapReduce or in Spark. It's called indices. Indices are what you have at the end of a book. Who has already seen in a book the last pages with an alphabetical list of words and you can look them up and find the page? Most of you, right? This is exactly what an index is, except that indexes predate computers. We already had them in books, but computers just do it in exactly the same way. So an index is just some sort of alphabetical list of values that allow you to look back the original documents. So why do we have that? Well, imagine we have billions of objects like that, and we have a query, find name Euler. That's called a point query because that query returns 1 document or very few documents. If you do that in Spark, it's going to take a lot of time. Why? Because in Spark, you have to scan through the entire collection. Turns out MongoDB is much faster than that with indexes. This is another example of query. Profession mathematician. Of course, there's a lot of mathematicians in the world, so it's not a point query. It's not very highly filtering. It would return a bit more people, maybe 1 million out of the billion. Right, but that's another example. So you see there's this notion of point query that is very selective and some queries that are less selective than others. Right. Here's another one that's called a range query. So this query looks for all the years that are greater than 1900. That's called a range query because it's not an equality, it returns an inequality, right? It's lower than, greater than, and so on. This also we can accelerate with indices. Again, who could do this in Spark? If I put these files on S3 and I ask you to do it in Spark, who could execute this query in Spark? I think almost all of you, right? It's basically a filtering, it would be a filter transformation with that criterion, and then you execute it, right? But it would take time. Okay. How can we make this super fast? And when I mean super fast, I mean, for example, that one, 2 milliseconds. As opposed to maybe 10 minutes or 5 minutes in Spark. 2 milliseconds for this. Billions of objects, 2 milliseconds. Sounds amazing, right? Magical. But actually, there's no magic, it's just technology, and I'm going to show you. So here's how it works. Here it's a simple example with fruits. Imagine I have every document is a fruit, and it has colors, and then I just, exactly like these pages at the end of my book, I just have this list of colors with the pointers. And if I look for a specific color, like orange, then that will directly give me the documents that have that color. Okay. But now let's do it with scientists. So imagine that I have this collection in MongoDB. You can imagine it's billions of documents, but of course I cannot put that in a slide. I'm going to build my index, and I'm going to build what's called a hash index. what's called a hash index. So in MongoDB, you only need to put that command create index on century. It's going to create an alphabetical list of centuries. I'm just using the analogy with the book, using a hash index. So here's what happens when we build the index. When we build the index, so here century is 20. So I have this magical function. It actually comes from cryptography. It's called the hash function. It's like a mixer where you put you put fruits in there and press a button and then juice comes out. It's exactly the same thing. It's basically like you put 20 in the mixer, press the button, and it turns out that 0 comes out of it. You don't need to understand how that works. It's just a mathematical function. It's deterministic. There is no randomness, but it outputs 0. So I'm putting 20 at position 0. You know that computer scientists, they like to start counting with 0. So we put 20 at position 0 with a pointer to it. Then 21. Oh, that's just a mistake. I put it with 20. But anyway, that's just a typo that I will fix. Then 19, H returns 4. And that puts me at position 4. So 0, 1, 2, 3, 4. And I put a pointer. Then 4, minus 4, that's antiquity. H returns 3. I put it in there with a pointer. And then again, I have minus 6 returns 1. And 20 again arrives here. So there's just a typo with 21. Imagine that it's 20 instead of 21. Okay. So you don't need to understand how this H function works. It's just a function. It's pure mathematics. It's just doing a bunch of addition and multiplication on things with some modulos and outputs some number that you use as a position in the hash table. That's called the hash table. What's important is that this function is super fast, H, right? Super fast. It's instantly returning that number. Who understands how we built that? Assuming I do have a function H, of course. Okay. Now here comes the query, because now we are done building the index. Takes a bit of time to build the index, but we are done. Here comes the query, find century 19. What do? We put 19 into the mixer, so into the H function. It's instant, right? Just call H and get 4 immediately. Doesn't take any time for that. Then you know you need to look at position 4 in the array, and looking at a position in an array is very quick in computer science. So it's very fast, just a direct access in the computer's memory. There you go, and you follow the pointer. And actually, it means that even if there are billions of documents in there, the query is instant, 2 milliseconds. All it takes is compute H, take the position in the array, follow the pointer. Who understands that? And it's also true if there's billions of documents. However, what's important is that there is no free lunch. The cost of that is that it takes time to build the index. It takes time, but it also takes space. You need to store it somewhere. So there is a cost, and in exchange for that cost, you get instant queries. Okay, now there's a couple of problems with hash indices. The first one is that they do not support range queries because they put the data all over the place. So if I come with an interval like give me all the people whose family name starts with an H or more in the alphabet, the hash index cannot do that. The hash index can only test for equality. So this is a limitation. Another one is that hash functions are actually not perfect. In real life, here you hope that there's no collision, right? There's 20 in a cell, minus 6 in another one. But in real life, if you have a large collection, at some point, you're going to have collisions with H. H is going to return the same integer for different values. It's fine, but then it slows things down. So just saying, it's not perfect. If you want to avoid these collisions, you can just take a gigantic hash table here, and then there's less collisions, right? But it has issues, which is the reason why you have a different kind of index that's called B+ trees. And these are actually very common in databases. It's kind of the basics of the basics that we teach in relational databases for computer scientists. They are super important. They also exist in PostgreSQL, by the way, hash indices and B+ trees. So what I'm teaching to you today is also true for PostgreSQL. Okay, so how do B+ trees work? Well, if you remember about these last pages of books, you shouldn't be surprised that a B tree or B plus tree is also kind of storing an alphabetical list of the values, right? So look at the blue cells here, almost, be carefully, so these are words in that case, taken from text. It's alphabetically sorted, right? So, of course, if you're a human and you look that up in the last pages of the book, all you need is the blue part. All you need is the list of words. Why? Because as a human, you learned in primary school how to look up words in a dictionary, and you do this with what's called binary search, right? You open it in the middle and then look, okay, it's before or after, and then you basically move along in the dictionary. So we humans are very good at spotting words in an alphabetical list, but the computer needs a bit of help. And the way we give help to the computer is by adding this structure above the blue cells. All of this is called a tree that allows us to actually find, right? So for example, if I look at the top, possess, I know that everything on the left comes before alphabetically, and everything on the right comes after alphabetically. You can easily check that, right? If you follow the arrows. Everything on the right is after, everything on the left is before. So that's called the B plus tree. The reason why we like to store data in that way is that the disks like to be accessed in blocks when you read the data from disk. And so you want this index to be structured in blocks, just like HDFS actually. One block is almost be carefully. Of course, there's more than 3 in practice, just because the slide is not big enough, could be 1,000 in practice. But basically, I have blocks of the alphabet that are stored on the disk together with pointers to the documents. Okay, so now very quickly, because again, this is specific for computer scientists, we love to go into the details of all of that. But there's just so that you know, the trees have the notion of depth, because here there's a depth of 2, right? You start with possess. That's the root of the tree, then 1, and then 2. They are all at the same depth, right? So these would be the grandparents, and then the parents, and then the children, right? So these are all grandchildren. Second, there are some conditions on the size of these blocks, and in that case, they have between 3 and 5 children, right? You can check 4 here, 4 here, except the roots that might have less. So the root has only 2. In the general case, so 3 and 5 is an example. In general, you can take d plus 1 and 2d plus 1 and put any value of d here, right? Okay. And again, it's fine. The root can have less than 3. Okay. Finally, the actual values, so what we want to sort alphabetically, they are at the leaves of the tree. So the leaves of the tree, it's what is at the bottom. They don't have any children, right? Okay, so the actual values are only at the leaves. And then every value here points to documents in the document store that have these values. Now, word of to be careful about is that you know that if I give you n trees, like for example, 7 trees, how many intervals between trees are there? If there are 7 trees, there's only 6 intervals, right? If I give you n trees, there are n minus 1 intervals. Okay? So it means that if I tell you that a node that is not a leaf, a node has 3 children, it means that it has 2 keys. That's the number of intervals. If a node has 5 children, then it has 4 keys, right? 4 values. Okay, who is following? Okay, so it means that if I tell you you can have between 3 and 5 children, it also means you can have between 2 and 4 keys. Okay, I have an animation now to basically show you. If I start now building a B plus tree like that, I'm going to insert in that case increasing integers. It's just an example, right? Doesn't have to be increasing in the general, but just for the sake of the animation. So 1, 2, 3, 4, and I'm going to assume that I want between 3 and 5 children, right? So between 2 and 4 values. Now I have 5 values. It would be 6 children if I put the arrows. So it's more than 4. What do? I split it, right? Cut it into 2 nodes like this, and I add a root on top, 4. I take 4 because it's in the middle, roughly. And now it's fine because I have 3 on the left and 2 on the right, okay? I continue, 6, 7, still fine. 8, I have a problem again. 8, that's more than 4 again. So I split it with 7, and that's it. Now I get again, now the root has 3 children, that's totally fine, 2 keys. Then I continue, 9, 10, 11. I again have more than 4. It's not a problem. I split it again. Now the root has 4 children. That's still fine. And now if I accelerate, let's go all the way to 16. Now I have, that's all good, right? I have 5 children on the root. Between 3 and 5 is fine. And I'm all the way to 16. But now what happens if I have 17? And I split it? But the problem is that now the problem is only propagating. Right now I have a problem with the root because it's not allowed to have 5 values. So what I do is I split it again, and now I get 1 more level of depth. That's the idea, right? So this is how a B+3 evolves, basically. So now if I do it concretely with MongoDB, and I take this collection right here, I'm going to start building the B+3 in the same way with the centuries. So create index century 1. If you don't say hash, but you say 1, it means that it creates a B+3. 1 means it's by increasing. It's like you have an alphabetical list increasing. Here it's numbers. It's not going to be alphabetical, of course, but you get the idea. Okay, so 20, 21, 19. So here, just because it's very small, I'm assuming that my parameter says I don't accept more than 2 values. Okay, so I'm going to cut it. Okay, then I have 4. That's again 3. I don't allow that. In that case, I want no more than 2. Then I add -6. Again, I need to split it. So I reorganize a little bit so that I find like this. And then 20. This is my B+3 now, right? And now I have a query that says century must be greater than or equal to 19. Now I've built my index, so I can use it. So what do? I look for the 19. Turns out that 19 is already on the top. I already know that everything on the left of 19 will be smaller than 19, strictly. So I can ignore what's on the left, right? There's -6, -4. I don't care, it's less than 19. And my query says I want greater than or equal to 19. So basically, I need everything on the right of 19. And now all I need to do is traverse my index and take the documents that correspond to this part. And I return these 4 documents. For whom is that clear? Okay. So a hash index is instant. A B+3 is not instant. It's a bit slower than a hash index, but it's still very fast. We say that it's logarithmic time, meaning that if you multiply the size of the collection by a factor of 10, it only adds a constant number to the time that you need, right? And if you multiply again by 10, like you go from 1,000 to 10,000, then from 10,000 to 100,000, it's still adding a constant time, right? So this is the magic of logarithmic time. Okay, so these are B+3s. So in practice, MongoDB gives you an index for free. You might remember this underscore ID that was on some slide. It's some automatic key that MongoDB adds to every document. It's like a number. You get an index for free on that. Just like in HBase, you get an index on the row ID for free as well. Okay, so if you want to build indices on other fields than this other underscore ID, this is called a secondary index. And that you need to tell MongoDB about with this create index. Remember this create index? Create index. That's how you tell MongoDB. Okay, so this is then called a secondary index. And what happens is that if you don't have any index at all, it's going to take time. MongoDB will have to read the entire collection, just like Spark. It scans through the data, takes a bit of time, filters it, and returns the result. But if you do have an index, that will accelerate things because MongoDB will be able to use the index to directly go to the relevant parts of the collection and only read these parts. It might need to do some more work in memory and filter further, but it will massively accelerate. So that's what an index brings you. Here's an example. Imagine I create an index, name last hash. It means it indexes the field last within an object associated with the field name on an entire collection. So assume I've done it. I already created the index. Then I call find name last Einstein. That's instant. 2 milliseconds, instant. Here's another one. I create an index on profession as a hash, and I try to select both on the profession and some other field that is not index theories. What's going to happen is that it's not going to be quite instant because you still need for theories to actually do some filtering manually, but profession, that will be fast. So what it will do is it will use the index to find all the scientists that are physicists, and then it will go one by one to only keep theories relativity. For whom is that clear? Right? So half of it is accelerated with the profession index, and the other half with theories is done manually. Well, manually, it's still a computer, but without an index. Okay, that's called post-filtering. Okay, here's another example. What's going on here? I have two parameters. I'm creating a B+3 index on birth and death. What happens here is that I first index on birth, and when I have the same birth year, then I look at the death year, right? So it's like the lexicographic order, right? So I build an index on the pair birth and death, but first I consider the birth and then I consider the death. For whom is that clear? Right? It's just one key and then another key. So then the query here that you see will be very fast. So not instant because it's not a hash index, it's a B+3 index, but it's going to be logarithmic, right? Okay. I can also change and put a -1, it would just invert the sorting order, right? I would sort by birth ascending and then by death descending. Okay. Here's another one that works well. If I create a B+3 index on birth and then I have a range query, that's going to work very well, right? Because my B+3 index supports range queries. It's just going to look up 1946 in the index, and everything that's on the right of it, because it's greater than or equal, will be returned. I can also add more here. That would be fine. It's just that death would not be handled by the index. That would have to be done after reading from the index. You just filter in memory. Okay. Here's another trick that works nicely, is that if I do build an index on birth and death, but I only query on birth, then if you think a little bit, you can use the index. Because if I look for birth 1887, it's like a birth-death interval. I'm basically looking for birth 1887, death 1887, all the way to birth 1887, death infinity, right? So this is why if I only use the first keys in a B+3 index, so birth, death, only birth, that's going to work and I can use my index, right? This also works. If I find every birth after 1980, whatever the death date, that's going to work. Okay, that doesn't work. And here it requires about more thinking. Why does it not? Well, it works, but it's not going to use the index. It's going to be slow. Why? Because if you look for scientists who died in 1887, what is their birth year? Could be anything before 1887, right? So in the index, it's going to be all over the place. There is no no easy way that you can look for the documents in the index. For whom is that clear? Right? And that's all because we first order by birth date and then by death date. Okay? All right. So that means concretely, and this is a misconception that many people make that mistake in practice, because when you build a collection in a company and you use a database, an important task is to select the right indexes to build, right? So that your website is fast. It's a science and an art to find the indices that you need. But a mistake that many people make is that they are overzealous in their indexes, and people might, for example, build an index on birth, death, and name last, and another index on birth date, and another index on birth date, death date. This is a huge waste of space. Why? Because if you have the index on the left, birth, death, name last, you don't need those on the right. You get them for free, right? All the prefixes on the first keys of an index, you get for free. So that would save you a lot of space to not have to build those on the right. Okay. So this is the end of the MongoDB lecture. Again, MongoDB is an improvement over PostgreSQL because unlike PostgreSQL, it can handle nested and heterogeneous data. Doesn't need a schema. It can have schemas if you want, but it doesn't need to. Just like PostgreSQL, you can import the data in MongoDB, Just like PostgreSQL, you can build indexes. Just like PostgreSQL, you can quickly execute point queries or range queries. Unlike PostgreSQL, it doesn't have a language like SQL, right? This is why we have the next part that is going to be exactly about having a language like SQL for either document stores, but also for data lakes. We'll see it for both. Okay. Are there any questions? Anything? Anything that is unclear, that you don't understand, that you want to elaborate on? Nothing in the lecture hall on Zoom? Does anybody have any questions? You have an opportunity. We have 5 minutes to the break, right? So there is a bit of time. Nobody on Zoom, all right? Okay, so I'm going to assume that it means that you understood, right? Again, no pressure on using MongoDB because you will not have a programming assignment on exam day, right? You will not have MongoDB on the exam machine. You might have Moodle questions where we show you a few queries, we ask you to what they do, or ask you questions about the index and so on. But you will not have to actually write JavaScript queries with MongoDB. Okay. Okay, let me gift you these 3 minutes. What would be very nice is you probably received this email on the evaluation. Did you receive it? Okay. So what they asked us is that we do it during the lectures to give an incentive that everybody actually does it, because we really need the feedback. This is based on the feedback that we can improve things and make the lectures better. There are plenty of examples of feedback. For example, in the past, one of the item of feedback was we need a textbook because there wasn't any textbook. And this is why we have a textbook today in the lecture. So this is an example of why the feedback is really useful and considered. So if you can, let's use the remaining 2 minutes to, if you haven't done so already, to open this link, to find the email, open the link, answer. And you can use the break. I will also give you a few more minutes into the second hour to start with that. So we'll come back at 1:15, but I will give you a few minutes to make sure that you fill the questionnaire, right? All right, so thank you very much. Again, if you want, you can do it during the break, but it's also fine if you just take the break to just do something else, and then again, we'll take time for the questionnaire after.
So just
yes?
One quick question on Zoom just popped up. Do indexes require a frozen database, or can they be modified on the fly when new data is added?
That's a very good question. You can also have indices if the collection evolves. So what's happening, let me give you an example. Imagine you already have a collection, has, I don't know, 1 million documents. You can say, build an index. You might have to wait for half an hour or so until the index is ready, right? Once the index is ready, the queries on the collection will be fast. What's going to happen now if somebody inserts something in the collection or updates the collection? What happens is that the index is incrementally updated. Every time you modify something in the collection, the index is adapted. It means that we are compromising on something else. There is another compromise. If you have an index, it slightly slows down the updates. Whenever you insert or delete or modify, if you have indices, that's going to be a bit slower because you not only need to modify the collection, you also need to modify the index. That's another price to pay for an index, right? So if you have too many indices, then you shouldn't be surprised if it takes more time to modify the collection. Did I answer your question on Zoom? Yes, awesome. And that was a very good question, very important point. So thank you for giving me the opportunity to say it. All right, so it's 9 a.m. So I'll see you at 9:15 a.m. for the remainder of the lecture. Thank you.